Hi, we are Team 7 and we're going to present our Hybrid Orbital Propulsion System, or HOPS for short. The team members are Michael Buss, Esther Choi, Jacob Gurula, Moy Kim Lee, and Stephen Scott. The team was advised by Dr. Nicholas Cernansky and Dr. Ying Sun. The smallsat industry is projected to increase six-fold in smallsat launches in the next decade. Also, it will have an average of $4.28 billion of revenue. This is a good motivation as a smallsat propulsion is still quite expensive and uncommon in the 1 to 10 kilogram range that our team is targeting. Our problem statement is to develop a simple, safe, and low-cost propulsion solution for smallsats for a variety of uses by university research groups and small businesses. So far, we have completed the designing of the engine and its subcomponents, as well as fabricating the prototype. What's left is to test the rocket engine and analyze the data. The design requirements for this project are based on the stakeholder needs. Based on our mission, it requires a minimum of 730 meters per second of change in velocity and a maximum payload of 10 kg for the smallsat requirement. From there, we are able to calculate the design parameters for a rocket engine, such as a thrust and oxidizer to fuel ratio. Since low cost and safety are our main concerns, we will use paraffin wax and oxygen for our fuel. Additionally, the use of the tangential oxidizer injection allows for the compactness of the system compared to the traditional design of the hybrid rocket engine. The following are the specifications and standards that we deemed applicable and followed through. Along with the standards, we also utilize the Falcon 9 Launch Vehicle Payload User's Guide, as well as the Rocket Lab Electron Payload User's Guide. A decision matrix was created prior to deciding which type of propulsion system was best suitable for our mission. 5 types of propulsions were considered, and they were each weighted and given scores based on the criteria. They include design simplicity, safety, thrust, size, cost, etc. After weighing in the scores, the hybrid rocket engine ended up with the highest score of 367 points, with cold gas propulsion following next.
The hybrid rocket engine itself is the culmination of preliminary design, CAD design, detailed analysis, and manufacturing efforts. Although manufacturing was almost entirely completed, testing of the engine was not performed because of the COVID-19 pandemic. Preliminary design was performed by deriving design requirements from the stakeholder needs, then performing iterative analysis and calculations in RPA, which is the Rocket Propulsion Analysis software, and MATLAB. These analyses provided the internal combustion chamber dimensions that were used in the CAD designs. Hand calculations were used for structural sizing of the combustion chamber components. Then, all components were analyzed in ANSYS to verify these hand calculations. Once design and analysis was complete, engineering drawings were created, and the parts were manufactured and assembled into the completed rocket engine shown in the center image. The top flowchart shows the design process that was used to create the engine. Stakeholder needs were converted to design requirements, then these requirements were input into RPA. Iterative analysis was performed in RPA, which provided outputs that were input into a MATLAB script that was written by the group. After iterating through several RPA and MATLAB analyses, the team settled on the optimal dimensions for the combustion chamber interior, as well as other engine parameters such as oxidizer and fuel flow rates and burn time. Once structural hand calculations were performed and the design was input into CAD, the entire structure was validated in ANSYS, which showed a minimum factor of safety to yield of 5. The engine features 2 paraffin wax fuel discs inside the combustion chamber. Oxygen is injected tangentially to create a vortex within the combustion chamber, which helps improve fuel regression rate. The combustion chamber housing consists of a central 304 stainless steel 6-inch Schedule 40 pipe sandwiched between 2 304 stainless steel custom-designed flanges. The flanges seal onto the central combustion chamber pipe with 2 high-temperature O-rings. Combustion gases in the combustion chamber exist at 3,384 Kelvin. They exit through the engine through a converging-diverging graphite nozzle, which accelerates them to 1,990 meters per second, or a Mach number of 2.17, at which point they will have cooled to 2,852 Kelvin.
To test the rocket engine and collect data, a test stand had to be designed and built. The primary purpose of the test stand is to allow the engine to be mounted and safely fired. Several other needs were taken into account when designing the test stand, such as the need for easy transportation, being generic enough to allow mounting of future engine iterations, as well as having the ability to mount several other subsystems to the test stand. Taking all needs into consideration, the team came up with a design that primarily features a 4-foot by 3-foot by 1/4 inch thick aluminum plate bolted to an 80-20 aluminum frame. As seen in the CAD rendering to the right, the test stand features a linear rail and bearing, which the engine is bolted to, a heat shield which protects the rail from heat and combustion products during firing, a safety wall, and a vertical steel plate called the load cell geometry, which holds a load cell during testing. Each component was designed to be easily added or removed from the test stand with only a few bolts. As previously mentioned, above all, the test stand must allow for safe engine firing. For this reason, the team used ANSYS to analyze a couple key areas of the assembly. The first of these areas was the load cell mounting geometry. This geometry consists of a thick, low-carbon steel bar bolted together with two pieces of steel 90-degree angle stock. Bolt pretension was applied, and a force 3 times greater than what the engine is theoretically capable of was applied at the location of the load cell. The resulting deformation was about 0.004 of an inch, and the equivalent stress was 15,000 psi, lower than the yield strength of material. The base plate, an 80-20 frame assembly, was also analyzed. Using the various subsystem weights and locations on the test stand, the base plate was analyzed for deformation. The analysis assumed that 2 people were carrying the assembly, one on each of the short sides. The resulting deformation was again very small. Based on these results, the team had confidence in the test stand design.
This is the piping and instrumentation diagram for the test stand and rocket engine. On the left are 2 K-sized compressed gas cylinders, which are used for gas supply. We are using oxygen as our oxidizer. Nitrogen is used as a purge gas to clear the lines of oxygen and stop the fuel from burning after testing. Blue represents oxygen equipment, green represents nitrogen equipment, and black represents any component that will experience both of these or a combustion product gas. The oxygen supply pressure is 2200 psi for a full K bottle. We will regulate it down to about 135 psig through a high flow pressure regulator. A 4-foot flex line will connect the pressure regulator to the test stand. The normally closed solenoid valve will act as our run valve for the engine, and flow can be tuned with a needle valve directly downstream. Next, oxygen passes through a check valve to prevent any nitrogen from flowing back into the oxygen supply system. A short flex line connects the test stand valves to the actual engine itself. This is necessary because the engine rides on a linear rail and rests on a load cell, shown by LCO1 in this diagram, and plumbing it to the test stand with hard lines would significantly affect the measured thrust. Then, the oxygen splits at a T and is divided to the 2 tangential combustion chamber injectors. It passes through 2 check valves so that hot combustion gases are unable to travel back upstream in the event of low-frequency combustion instabilities. We will measure chamber pressure and pressure upstream of the injector check valves. Since we know the flow coefficient through the injector check valves, we can use this differential pressure to calculate the oxygen flow rate. Temperature measurements will be taken on the exterior of the combustion chamber and the nozzle to compare with analysis results and ensure that the design temperatures of any components are not exceeded.
As we have mentioned in the design requirements, we use paraffin wax and oxygen as our propellant. We chose the paraffin wax as our fuel because of its non-hazardous properties and high regression rate. The oxygen was chosen as an oxidizer because of its combustion performance and relative safety as compared to other oxidizers. To test the wax for our fuel disc, we created 2 silicone molds for the front and the back fuel disc. The silicone mold provides an easy release to the paraffin wax in addition to being reusable to make a large quantity of the fuel disc. The images on the right show the silicone mold and our casted fuel disc. Above the images is a balanced equation of the paraffin wax and the oxygen. Carbon dioxide and water are being released as a result of the combustion. Additionally, energy is also being produced in the form of heat during the process.
To safely control the rocket engine during testing, a control subsystem was needed. The figure on the right shows a schematic serving as the basis for the construction of the electrical circuit. An Arduino Uno is used to process command inputs and manage 3 outputs. Shown above the Arduino from left to right, these outputs are referred to as the oxygen supply control, nitrogen purge control, and the ignition control. The oxygen supply control uses a logic level MOSFET to allow the Arduino Uno to open and close a solenoid valve to allow gaseous oxygen into the engine. The nitrogen purge control is identical to the oxygen supply control in design and allows nitrogen gas to flood the rocket's engine's combustion chamber at the end of the test. Finally, the ignition control supplies 1 amp of current to an electric match inserted into the nozzle of the engine. Passing current through the electric match burns a combustible material at the tip of the wire, which provides the spark for the engine to light. Following the assembly of the circuit, a housing was fabricated to protect the electrical components. Additionally, this housing provides a platform to mount the input controls and indicator lights. On the left, a top view and isometric view of this housing can be seen. To begin testing, first the key lock switch is turned to the on position. This powers the system on, and if all components are properly connected, the green continuity light will appear lit. When ready to fire, the user will flip the toggle switch to the on position, which runs the firing protocol coded onto the Arduino. In response, the red light in the middle will turn on, indicating that the solenoid valve is open, allowing gaseous oxygen to flow into the engine's combustion chamber. Shortly after, the electric match will combust, igniting the engine. After a specified amount of time, the solenoid valve will close, shutting off the oxygen supply as the nitrogen supply is opened. When finished, the user turns the key lock switch to the off position to power down the system and conclude testing.
A number of different materials were used in this project. To highlight a few, graphite rod was used to make the nozzle, 304 stainless steel was used for the combustion chamber, 6061 T6 aluminum was used for the test stand, and low carbon steel was used to make the load cell geometry. In terms of software, the major programs used throughout this project were MATLAB, SOLIDWORKS, Arduino IDE, Rocket Propulsion Analysis or RPA, and ANSYS. Starting early in fall quarter, the team began designing parts in SOLIDWORKS and performing analysis in ANSYS. After months of hard work, the team had completed CAD of the engine, test stand, and most subsystems. At the start of winter quarter, manufacturing was underway. The team machined parts, tested an ignition system, created molds for our fuel discs, and completed numerous other tasks. Shown in this picture are the prototypes the team had completed at the time of the winter poster session. They include the engine with epoxy lining and piping, most test stand components, an ignition control system, and wax fuel discs. Several additional parts were manufactured after the poster session, but unfortunately, due to the rapid COVID-19 shutdown, the team was unable to take a picture of all completed prototypes.
With the COVID-19 pandemic situation going on, our team had to cancel our testing plan for the spring quarter. Since we could not test our prototype, we performed additional analysis to validate our design instead. Some of the analysis that we did are nozzle thermal analysis and oxygen feed system analysis.
RPA provided thermodynamic, chemical, and gas dynamic parameters for the rocket engine at different points such as the nozzle inlet, throat, and exit. It estimated actual rocket engine performance as compared to theoretical performance, and it allowed us to perform rough sizing of the converging-diverging nozzle. Some of the outputs from RPA were used as inputs to a MATLAB script that the team wrote, and another MATLAB script that was used for determining the optimal converging-diverging nozzle profile. The team's MATLAB script accepted 13 inputs, such as specific impulse, thrust, and chamber pressure. From those inputs, it calculated other parameters such as fuel and oxidizer mass flow rates, required propellant mass, fuel disk dimensions, combustion chamber dimensions, and burn time. The team also used another MATLAB script which calculated the optimal nozzle contour and performed two-dimensional CFD on the diverging section of the nozzle. These CFD results were used to verify some of the RPA outputs. Once the CAD design was complete, structural FEA was performed on each part to validate structural performance. The lowest factor of safety to yield on any part was 5, which is very high for aerospace applications, but was desired for this ground-based prototype for safety reasons. During the spring quarter, the team was unable to perform testing due to the COVID-19 pandemic. Instead, the team continued work by performing remote analyses. A steady-state thermal finite element simulation was performed on the nozzle to quantify temperatures and heat fluxes through the graphite nozzle throughout the burn. Steady-state temperatures for the nozzle were within an acceptable range, and although some throat erosion is expected due to graphite burning, the analysis showed that the nozzle will not melt and adjacent parts will not overheat. An analysis was performed on the oxygen feed system to quantify the pressure drop through the fluid components. This analysis showed that pressure drop is nearly negligible at less than 1 psi. Additionally, it showed that choking will not occur through any feed system components. The maximum set pressure of the pressure regulator is several hundred psi higher than the engine chamber pressure, so there should be no issue with meeting the required engine chamber pressure and oxidizer flow rate. Several lessons were learned throughout the analysis efforts involved in this project. Often, redesign in CAD was required after analysis or testing results were compiled. In several cases, the team was able to cross-verify results of separate analyses in order to improve our confidence in their results. For example, we cross-verified thermodynamic and gas dynamic properties between our 2D nozzle simulation and the RPA analysis. Even with this verification, it is important to always test to verify analysis results. One example of a situation in which analysis results did not match physical results is for the finite element analysis performed on a stainless steel ring which clamps the nozzle to the rest of the engine. This part is shown in the image on the right side of this slide. Analysis showed that deflection of this part was very low and within an acceptable range. After manufacturing and installation, we found that the part was visibly deflecting under the bolt loads that were applied to it, so we had to rebuild the part with twice the original thickness. Physical testing of the engine as a whole needs to be performed to validate other analysis results.
Different factors such as economic, environmental impact, social impact, and ethical have shaped our design. Economic. The annual revenue of the small set industry is estimated to be $4.28 billion, and the prototype of the engines would cost approximately $4,300 to build. Environmental impact. With the use of non-toxic propellants, the engine will not create any hazardous waste or significant amount of industrial pollution. Additionally, depending on the mission, the engine will deorbit upon mission completion and burn up on re-entry to mitigate the issue of space junk in the orbit. Social. With the low cost of small set propulsion, the university research lab and small businesses are now able to launch small set on their own into the orbit. The need for mass production of the engine will also create job opportunities for the public. Ethical. We put a lot of emphasis on safety as providing a safe propulsion system is one of our main goals. With the hybrid rocket engine, it can be shut off in the case of accidental ignition, whereas other type of rocket engine, like the solid fuel rocket, will continue to burn until all fuel is spent.
Over the course of senior design, the team accomplished many of its goals. The highlights from the past year include securing over $4,800 in funding for the execution of this project, designing and building a prototype engine, test stand, control system, and propellant discs for full-scale testing, and performing detailed analysis to learn about engine functionality and feasibility. Reflecting upon the past year, the team learned many lessons along the way. Formal design reviews would have been beneficial to the team to minimize future complications. Design is an iterative process, and prototyping takes longer than expected. Time management is especially crucial in such a tight project window. Working as a team opens the door for conflicting opinions and healthy compromises, but this experience is also very rewarding to each member. Without each member of the team, the project never could have been as successful. Finally, when communicating with professionals, consideration must be made to pay extra attention to detail and regularly follow up. Maintaining an open pathway for effective communication takes effort and intent. Lastly, the team felt there were two areas in which the senior design course could improve. First, teams could be formed in MEM-391 in the junior year so that they can better hit the ground running in MEM-491. Also, it would help students if they could spend their own earned funding themselves through a Drexel monitored portal. This would make bookkeeping easier and help students keep track of parts ordered, shipping charges, and arrival dates. The team secured funding from two sources to finance the project. $500 from the Mechanical Engineering and Mechanics Department Senior Design Grant and $4,309 from a Pennsylvania Space Grant Consortium mini grant. This money was used to cover the total prototype cost, which amounted to $4,374.98. To summarize the year, the team was able to overcome numerous technical challenges in a short design period. We are disappointed that we were unable to test the HOPS engine, but hope that the project can be completed by a new team in the future.
Our team would like to take a minute to thank some of the people who helped us with our project along the way. First and foremost, we would like to thank our advisor, Dr. Cernansky, for his unwavering support of the team. Whether it be attending a weekly meeting, offering guidance, reviewing our submissions, offering lab space, or communicating to university staff on our behalf, Dr. Cernansky was always there for our team, and for that we thank him. Additionally, we thank our co-advisor Dr. Ying Sun and our senior design coordinator Dr. Ashison for their guidance throughout the past year. We also would like to thank the NASA Pennsylvania Space Grant Consortium and the Drexel MEM Department for their generous financial support of the project. The team also thanks Mark, Scott, and Nick from the Drexel Machine Shop, as well as lab manager Ray Dobbins for their assistance and advice throughout the fall and winter quarters. Last but not least, we would like to thank Lee from Dr. Sun's lab and Julius from Dr. Cernansky's lab for their help throughout the year. Without everyone on this list, our project would not have been possible. And lastly, here is a list of references that were used in this presentation. On behalf of the team, thank you very much for watching and listening to our presentation.